optimization process. So imagine you are part of the technical staff of how to say, people who manage a smart city, and there are a lot of very huge amount of diverse data here that are located in different places, and that they use a lot of different computing devices. And the problem here is how to do this efficiently. So you can use all tools that you know from operational research. And there are many ways. So you can use contrast programming, you can use intelligent linear program, or whatever approximation algorithms are concerned here. And but okay, as we will see, probably for some reason, it's a big, very difficult problem that could probably, when you are going through practical issues that are not always very efficient, due specifically to some uncertainties over the data. And I would like also to put something, emphasize right now on some topic, which is there are some power limitations, and all our the red line of our talk will be on power limitation, as you will see. So just with a small picture, it's like you have this smart city here, and we are interested here in what is completely hidden part of this big iceberg here. That are all the connections and all the electronic and computing devices that are behind, and that makes things running well. Okay, so here just this small example here just illustrates our invasion of our world here, of this digital world in our lives. And obviously, you know this because there is an ever increasing number of such devices, very diverse. And actually, the impact over the emission of CO2 and is about few percent, but with a very big annual growth, which makes this growing exponential. So it's a big problem if we just are going 10 years ahead from now. And obviously here, what talk here right now is a research management problem here, keeping in mind all this problem in using too much devices that are growing very fast. Just a small picture here. So what does it tell? Here you have some blue side of the graphic of the Gantt, and the orange side. And this is somehow the repartition of all the digital components. That makes here somehow a balance between production of these devices and usage of these devices. And as you can see here, there are some terminals, data centers and HPC centers and networks. It's rather a good balance, but it shows more or less the repartition. Okay, what is a small summary of this short introduction? This is always more diverse, powerful, larger, and to go what could be done using machine learning to help taking good decisions here. Okay, and the roadmap here of our talk is first, I will take some time, maybe 10 minutes, to present the parallel distributed computing domain. That is the main domain we are working on, and the scheduling problem, which is a central problem here. And then when we meet machine learning here, so we did not develop somehow the most common approach, which is somehow computing and optimizing something to support machine learning. So there were a lot of studies at the very beginning by taking an algorithm in machine learning and optimizing it in GPUs or sets of GPUs. But we are just developing some hardware, dedicated hardware. We are not in this stream of thinking. We used machine learning in a second kind of approach that is the tool for helping resource management. And there will be three here experiences. So Danilo will discuss the first systematic solution, and Salah will discuss the two other solutions, and then we can from these three experiences just discuss with you and go and asking about the limits of machine learning. Okay, so then let's go to the parallel and distributed computing. So I will not be too long. So even if people who are very easy in this field, you can probably stay here. Okay, so here this is the first slide, just to see that the landscape is very diverse, and we will focus on HPC. HPC is high performance computing. Why? Because we are coming from this field, and it's rather easy, let's say, way of doing parallelism, because somehow the things are not too complex, as you will see. Okay, in this field of HPC, we have something that here twice a year. This is a big meeting, and we are talking about what they call the top 500 ranking. Here, this is a kind of contest, and that gives the most powerful machines over the world. So it's quite interesting here, because we are a bit more than the exascale. Exascale is 10 to the 18 flops. Flops is the measure of floating point operation per second. So it's a very huge power. And you will see here with the dot line just on the top, that the best machine. Then this is the number one. Number one is a triangle, and the summation is the circle at the top, and the other one, the curve below, is the number 500. So this gives you an idea of how the power is growing. Okay, so this is just a picture of the first machine, the top machine in the last ranking last June. It is in Japan, and name is Fugaku. But here is another thing which is quite interesting. We can see also what's the contest in terms of power consumption, and this Fugaku is still in the rank, but it consumes a lot, and consumption is given by gigaflops per watt. And you see that the top green machine is only 170 on its performances. So these are some order of magnitude of what happens. And just Europe, the whole Europe is behaving quite well in terms of green computing, because the Atos, which is a French company with some AMD, which is a Great Britain company, did machines that consume not so bad, and the ranking is very good. Okay, so now what about so this was the landscape of the machines today. So we are typically focusing on this kind of big clusters. And now let's go from this hardware and organization to the job and resource management system, which is handling all the scheduling and allocation module. So you have an application. The application is represented by a task graph. Typically, a task graph is some operations, and the data are useful for some other operations. So you know probably this. And you put all this into boxes where you put as a vertical axis the number of resources, and as a horizontal axis the expected time that you expect for executing this graph. This is the basic tool, as you will see. This is a real graph here, a small one, but a real graph typically. And here is the result that of a very small one run, because it's only 130. This is on our cluster here, and you can see here small jobs and large jobs, or very so you have very narrow jobs that occupy the whole machine, and you have to organize all this automatically. This is somehow the scheduling problem. And now maybe with a picture you will understand more easily. So we have a set of users that developed some applications, and typically this user here is submitting a job here at some point of time here, and all the jobs here are queued in the submission queue, okay, with so keep in mind the Gantt chart of last slide. And then all these jobs here, the ordering of the queue is managed by what we call the scheduler. Scheduler just keeping in mind what is the monitoring of all the resources at some point, what are the occupied resources, what are the available ones, and you run some data analysis and some algorithm on jobs profiling. And the idea here of the scheduler is to output the job allocation and, if possible, with some optimization, not only on performance, it could be optimization on good usage of green computing, less resources typically. And then taking into account all this, it's given to the machine. And here you have the result that comes back to the users, and the users can use the results in order to prepare a next run, because obviously you don't develop programs in such big machines only for one run. And the cycle goes on. Okay, so this is what, how does it work? So more, not formally, but we have to answer both questions, where and when. And the scheduling problem is to answer both questions. Okay, now here, how to solve this scheduling problem. So we have a lot of theoretical studies. We can have approximation algorithm with bounds, with you can use integer linear program, some new techniques like dual approximations or dual fitting, whatever. And you have a completely different side, which is a practical side of what is running on this system practically. These are very simple heuristic, as you will see. I will develop one here, and we will give the experiments according to this simple heuristic. So how does it work here? At the top right of the figure here, you have a job J. The duration, the real duration of the job is called Pj, and then you have Pj tilde, which is here the expected running time, and you have the set of resources here, Qj, that is needed to perform the job. Let me consider only a very easy example with only 2 machines here and 3 jobs. 3 jobs are described here. Here, R is a release time. That means the time where the job arrived in the system. First job arrived time 0, second time 1, and the third time 2. So these will be queued in the submission queue. And then resource requirement is 1, 2, 1, and the request running time, which is a upper bound of the real running time, is respectively 5, 2, and 2.5. Okay, so at time 0 there is nothing. So the first job is coming. Then the duration is 1. The number of machines required is 1, and the duration is 5. So then we reserve 5. Okay, and here I just put in gray the difference between the actual running time and the expected one. And now here at step 2, here step 1, okay, just 1 unit after. The second job is released, but here we reserved all these 5 units of time for the job 1. So then 2 cannot be executed before this time. Okay, remember, we don't know when will be the real direction, the duration. We will know this only at the completion of the job. And then we continue here to run. The job 3 is coming here. So here the policy what I'm describing is easy backfilling. BF means backfilling. And here the 3 is somehow later. Okay, there are two jobs in the queue, 2 and 3, but 3 comes later, but can be executed because here there's enough rooms for doing this job before without any delay on job 2, on the reservation of job 2. So we can start executing job 3. And this is step 3 and step 4. And at step 4, we know that both jobs complete. Okay, then the job 2 can be shifted behind here. and it can be start its execution right now instead of what was expected at 5. Okay, because the resources are now available, and we continue here, and at step 5 it is completed, so we have the full execution. So this is what we call the easy backfilling. And easy backfilling, you can put any priority ordering of the jobs, and the most common one is first come first serve, FCFS. And so this is very somehow not stupid, because it guarantees that there is no starvation in the system, because you will always do a job because you take them according to their arrival dates. So but it's far from optimal, and you can, from the theoretical point of view, see that this policy is arbitrarily bad. Okay. Why? Because it's we don't know anything about the information of the job somehow. We just take the release dates. Please notice also that there are a lot of parameters that vary during this execution. And now here comes, we don't know about the real duration of the jobs. We just knew about what was expected. Okay, again, it's an upper bound of what is the reality. So now, how to manage uncertainties to better know the habits of the users or the jobs that are submitted. It's possible, yes, and machine learning looks perfect for this task. So let's investigate this. So here, just some hypotheses here. So we don't know when a job will arrive. Okay. Maybe we can have some expectation, but more or less here this is why HPC example is rather good example, because the resources are more or less known in advance. You don't have any process that crashes, or usually you have very small uncertainties here. And but the execution duration are again, they are given, but they are not. We know that they are not accurate. Okay, so now I will just drop some few words about a vision of machine learning from people who are not from the field. So probably people who are very aware of this will react. Okay, let's see. So what is so machine learning? Is something that is very well known now, so I don't want to discuss this, but maybe it's interesting. Let's discuss our view. So for us, there are 3 reasons of the popularity of using machine learning. At least this is something that we experienced. Our first experience in machine learning was in 2014. So then, why it's so popular? Okay, because now we have very powerful parallel machines that are able to have a lot of big performances. Okay, even usually the machines have some accelerators like GPUs, TPUs, and there are also a lot of data available, which is very good for machine learning, because the more the data, the better the analysis somehow. And this is a very easy to use somehow. There are efficient libraries, on-the-shelf components, so you don't even have to develop anything. Just take from the web, and you run random forest, supervector machines, or whatever, even neural networks. And third, it works in practice. This is why people are using a lot. Okay, just one slide about for us the idea of the roadmap of machine learning. Somehow, before 2012, there were only very dedicated applications and nothing else. And what I call special purpose machine learning, you're just guessing a character or recognizing very simple stuff. And then there was the first GPU boards, where people found that machine learning can really benefit of this kind of board and vector machines. And then there was a big development. This was at the end of this period that we moved to this field a bit. And then from this, we have always the same tendency with tens, a lot of GPUs that are connected together to reach big performances. And we reached a big performance in 2016. And then we even have now, from a few years, dedicated coprocessors with massive parallelism. So now we have in France the Gen C machine with 1,000 of GPUs, for instance. And there are now a huge development of publication using ML in all fields, humanities or art, design, whatever. So everyone is doing machine learning. Just press a button and you have your result. Okay. And this is also, we have a good tendency right now, even with the better cost, better ratio with flop over watt. So that means all these components are greener. Okay, now maybe I will give the word to Danilo if you are ready, and I will just now. We will report 3 experiences of using machine learning for the sake of scheduling. And after this, we can have this discussion over all what we found about all these 3 experiences. Okay, so maybe Danilo, you can, could you share your screen?
Yes,
you want me to stop this one, right?
Yes. Okay, share screen. Share screen. Okay. I think, is it okay? Are you guys seeing the slide number 36?
Yes, it's fine.
Yes. All right. So hello, I'm going to briefly introduce our first experience into using machine learning into scheduling. And in this first part, we try to create new ways to sort the waiting queue. As Denis mentioned, we the most used the way to sort the waiting queue in easy backfilling is to use first come first serve. And now at this first approach, we try to see, okay, let's see if we can use machine learning to create new ways to sort these the jobs in the waiting queue. And for this first experience, we created a 2-step approach. So in this the first step, we used simulations to try to observe the scheduling behavior under many different situations. And for each of these situations, we collect data, and in the end, we construct a data set with the observations that we find in the observations in the simulation. Sorry, and in the second step, we use this data set that we created in the simulations to create a model that better represents the observations that we found during the simulations. And the hypothesis here is that a good model, a good fitting model for this data set will be as well as good scheduling policy. Will sort the jobs in the waiting queue in an efficient manner. And okay, so how do we created the data set? So for this task, we considered scheduling data that is present in a workload trace. So in these workload traces, we have information about the jobs, such as arrival times and the processing times, the estimated, the requested processing time, and the number of processors of the jobs. So we take this whole workload trace into account, and we separate. So we get this trace, and we divide the trace into many pairs of sets, of jobs. So in each of these pairs, we have 2 subsets. So the first subset of jobs is the subset that we call the warm-up, and the other subset we call as the queue subset. And with these 2 pairs of sets of jobs, we set up a simulation environment. So jobs from the warm-up set will be the jobs in the initial state of the platform during the simulations, and the jobs from the queue will be the jobs on the waiting queue during the simulation. So given this scenario, this configuration that we established, a question that needs to be answered is, which job from the waiting queue must be chosen for execution in order to you have to optimize for a certain objective. And here we are using we considered the average bounded slowdown objective function, scheduling objective function. So with this setup, now we perform many simulations of this configuration. But at each repetition of the simulation, we choose jobs from the waiting queue for execution, taking them in a different order. So each repetition will be a different ordering of the waiting queue, just to see, just to actually see what happens in the scheduling performance if we choose different orderings of the jobs in the waiting queue. And for each of these repetitions, we compute as well the performance of the scheduling for each of these repetitions. And after we perform many repetitions, for each of the jobs of the waiting queue, we compute a number that we call the score of the job. And the idea of this score is the lower its value, the better was the job, the better was the choice of a certain job to be chosen for execution, taking into account the objective. So for this example that I showed here, we end up having a small table with the information of the job's characteristics, the processing time, the number of processors, and the time that job arrived, as well the score value that we computed during simulations. And this score value means more or less as well like the importance of this job to be selected for execution. And okay, so taking into account many distinct pairs of warm up and queue, we end up having a large data set containing the characteristics of the jobs and the score values that we computed, that we observed during the simulations. And now the next step is to take into account this data set. We need to create a model that better encapsulates, better represents the observations that we found during these simulations. And for that we used machine learning. Okay, so how do we create these models? So first we define a search space of possible models, possible scheduling policies, and for each of these functions of these models that are present in this search space, we used a nonlinear regression to fit these models into the data set that we created during the simulations. And after we performed the nonlinear regression, we just selected the best models in regards to the data set. And here again, the hypothesis is that these best models will perform good as well as scheduling policies. And now, and our task is to evaluate them in regards to scheduling performance. Now here, just to summarize a little bit of the results that we obtained during our experimental campaign. These are the 4 best functions that we found during our experiments. And for these functions F1 to F4, we considered a workload trace, a synthetic workload trace. And here are functions F1 to F4, which, well, they are mathematical expressions of the job's characteristics, the processing time, number of processors, and release time of the job. And they are quite similar, meaning that they are sum of 2 components. So the first component being the multiplication of the processing time and the number of processors, and another component is the release time of the job multiplied by some large constant, which is, well, that's interesting. And now, since we obtained these 4 functions, and our next step is to evaluate them as how well these functions can be to sort the jobs in the waiting queue in easy backfilling. So for that, we considered functions, these functions F1 to F4, and we performed we performed several simulations to evaluate these functions as scheduling policies. And for this evaluation, we consider the workload scheduling data of many different real-world platforms. So here I'm describing these real-world platforms that we considered that we take data to evaluate our policies. Here are the main results of this first experience. So in this set of graphs, we show the performance of the scheduling policies, taking into account many distinct platform data. So we used here, we tested our functions F1 to F4, and we also compared them with some policies that we can find in the literature, and as well first come first serve, the main sorting function of easy backfilling. And the idea here of these graphs is the lower the box plots are in the y-axis, the better was a certain policy to schedule the workload. So as you can see here, our functions F1 to F4, they were quite efficient in our evaluation to schedule the workload and take into account the data of these distinct high performance computing platforms, and significantly more efficient when we compare them to first come first serve, which is quite interesting as well. And another interesting observation is that our functions F1 to F4, they were created taking into account a generalized synthetic workload trace. So we can maybe think here that our functions these functions, sorry, these functions F1 to F4, they were not created taking into account specifically these platforms in particular. So we can maybe think of a certain generalization capabilities of these functions F1 to F4 to perform scheduling. And okay, to conclude, so here we did the first step to use the scheduling data that we have and machine learning to create new ways to sort the jobs in the waiting queue in a high performance computing platform. And we generate an interesting way to generate data and then use this data to create functions. And at this first step, we try to create simple functions. And well, simple here means that these functions are mathematical expressions of the job's characteristics, but there's some things in these functions that are still left to be explained in terms of scheduling. For instance, if you look back at functions F1 to F4, we see, for instance, square roots and logarithms and big constants. And in terms of scheduling, what these components mean. For instance, what's the square roots? Why is the square root is important for scheduling? For instance, it's not trivial to find an answer for this question in terms of scheduling, and these are the main probably drawbacks of our approach. But well, as I mentioned, this is just the first step that we did. And now my colleague Sala is going to present a more sophisticated approach into this problem of resource management and using machine learning into resource management in HPC. And Sala, you're more than welcome to. I'm going to stop sharing here. You can upload your presentation.
Excuse me,
Okay.
you have two questions in the Q&A. I don't know if you want to answer them now.
Wait a second. Are you? Yeah. Are you okay? Which machine learning algorithms we used in this approach? So we used for this approach we used this nonlinear regression, and so we generated many models, and we used least squares fitting to fit a certain function to this, taking into account the data set. But it's very simple regression problem using nonlinear least squares fitting. It's quite simple. I think that's the question. The first one I think is for me, but I'm letting Sala present.
Okay. This is. I'm trying. There's something wrong with my navigator. 1 second.
You have to share your screen.
Yes, I'm trying to share the screen, but apparently there is something wrong with the application that I have. 1 second. Let's try now.
While he's trying to share his screen, maybe you have two other questions, and Denis or Danilo. There are two open questions in the Q&A.
Yeah, I think I can answer.
Hello, so I'm taking the token here. So, okay, so this is a very interesting question about reinforcement learning. Actually, we are doing this currently with some people in Athos. And the idea here is, so maybe you know about what is a reinforcement. That means you will look afterward about some results and give some reward to some operations that were good. Okay, we are investigating this, but we don't have still right now any result. And about the first question, I'm sorry because Lionel asked something about gigaflops. And okay, you know, just the top 500. This is you have to benchmark your machine according to a set of benchmark that are given for a while, because it's more than maybe 30 years ago that they started to benchmark all the supercomputers and the collection of linear algebra kernels, whatever. And this is obviously the hardware and the software, but this is the way you fit your all this benchmark to the specific software of the machine. This is why, for instance, the machine at Riken, the Japanese machine, are especially well fitted from the software point of view, with the size of the registers or whatever. Okay, so I think maybe it's okay, or okay. And I will share the screen. Je vais share the screen. Tu me diras les choses. Okay, I will now share the screen for Salah. Here. Okay, let me do this. Okay, probably you can see what happens now.
Yes, we see the screen.
Oh, so why is it? Okay, so this is a small. Okay, let's go.
Should I go there?
Juste ça.
Just mute on your microphone because there is echoing.
Mets la caméra. Enfin, vas-y. Voilà. Vas-y. C'est bon?
Hello, can you guys hear me?
Yes, we can hear you. Go ahead.
First of all, I'd like to apologize for this inconvenient technical issue, but here we are. So now I'm gonna start. For the second experience, we decided to combine job characteristics to generate scheduling policies. This approach fundamentally is not very different from the one that Danilo just presented. First, I will start by defining what the concept of mixed policies. It's basically a method that we devised to dynamically generate scheduling policies that adapt to the workload. Via this method, we showed that it is possible to generate policies that significantly outperform simple scheduling policies by a simple mixture of job features. And again, via this method, we managed to study the nature of the available data and gain some available insight about to try to answer the fundamental question whether or not it is possible to apply online learning to scheduling data. I will start by properly redefining index policies. An index policy is basically a rule used to order the jobs in the waiting queue. In easy first come first serve, for instance, the rule is the jobs that come first are served first, as the name entails, first come first serve. Index policies are built based on a certain characteristic. We can also call it feature that is shared between all the jobs. Denis, in the beginning of the presentation, presented the three fundamental characteristics of any job: the requested time Q, the requested or estimated processing time P, and the actual processing time, and the waiting time. From those three core features, we can construct any number of features we want. Here we offer three examples: the estimated ratio, the estimated area, which is the requested time multiplied by the requested resources, and the estimated slowdown or expansion factor, which is how much the job spent in the system, the waiting time plus the requested time divided by the requested time. And from these 6 features, we construct 12 policies. For each feature, one policy to order by the smallest, one to order by the largest. So we have first come first serve and its opposite, shortest processing time first and its opposite, and so on and so forth until the end. Here I highlighted the 3 most important ones for the sake of this presentation. First come first serve because it's the baseline that we will compare to. SPF and SAF simply because they seem to outperform all the other policies and all the tests that we performed. Okay, now we will define what a mixed policy is properly. We represent a job by a vector of characteristics: Q, P, waiting time, ratio, expansion factor, and the area. And for each job, we attribute a score. A score basically the sum of the weighted linear combination of all these features. Basically, a score of job G is W transpose time G. W is the weight vector. And after calculating the score for every job, we order them based on the numbers. For the sake of simplicity, in this presentation, we will work only with select only 3 features, the 3 core or basic ones: Q, P, and waiting time. So the score of a job G will be W1 QG plus W2 PG plus W3 waiting time of G. So the major question is, after defining what a mixed policy is, how to determine the best set of weights we can take in order to minimize the objective function as much as possible. Here I take the same objective function that Danilo defined previously, which is the average bounded slowdown. For this, we use 2 methods. Each one of them serves a goal that I will detail in due time. First, we perform what I would call a brute force search, which is basically a uniform discretization of the search space. This method results in roughly 8 times 10 to the power of 6 points, and each point represents a simulation on a scheduler. And the other method, which is faster, which is used to directly find the optimal, which is using some basic black box optimizers, think simulated annealing, AMAES. But for this work, we decided to choose XNES simply because it outperformed all the others. Okay. Unlike the previous experiment, the one that Danilo presented, we decided, from a data point of view, we decided to go simpler. We do not use any synthetic data. We do not use any reshufflings or or external sources of data. We just use the workload as it is. We take one of the workloads and we divide it into several weeks, independent weeks, and we perform our simulations on weeks independently. More precisely, if you want, for each week we perform our simulations and we optimize them, for instance, using the exponential natural evolutionary strategies, XNES, and from that we obtain the optimal for each week. And after obtaining the optimal, we compare the results. Okay, this is a lot to unwrap, but bear with me. First of all, the x-axis here, the x-axis represents the time, the weeks, and the y-axis is the cumulative bounded slowdown, basically the cumulative value of our objective function. The first note, which is not surprising to anybody, first come first serve is a bad policy by all means and purposes. So we will exclude it from this analysis. We will focus on the remaining three. You have SAF, which is according to our experiments, nearly all of them, it's the best simple policy to use. We compare it to the best pure policy, which is the policy that you obtain if you choose the single best policy of the 12 that I just presented in every week. And W star, which is the result of individual weekly optimizations using the mixed policy method that I presented. You can see that there is significant levels of improvement that can be gained by moving from one level to the other. If this one, from moving to a simple static policy to choosing one of the simple policies, the best of the simple policies, or from choosing one of the best simple policies, basically from choosing a discrete policy to choosing one of the mixed policies that we try to optimize, try to fight via optimization, sorry. But the question is, as you might have guessed in the previous, when I was presenting them, the W stars or the optimal policies are detected offline. Basically, we take all the data available in a week after it's finished, and we run our simulations until we find the best policy. But the question is, can this be done in an online manner? Meaning, can what we learned from previous weeks be transferred to future weeks? Well, the answer to that question is basically yes or no. It's a little bit more complicated than a binary answer. In this where our brute force method come to play. We decided to visualize the entire search space, at least for our three dimensions. You have the Q, you have the waiting time, and you have the P. I will not go into too much details about how we constructed the search space due to time constraints, but just know that this is the landscape of our entire search space. The lighter the area is, the more optimal the results are. The darker the area is, the less optimal are. The red dot represents the absolute optimum, W star basically, and the blue triangle here represents the optimal that we obtained on previous data, basically which we will call W train for convenience purposes. These results were obtained for a certain week of a certain trace. If we move to the immediately following week, we can see that the search space completely changed. The optimal position also changed drastically. We move to the next week. The same observation. This one doesn't change because it has been already trained, and we do not perform retraining. The following week, the exact same observation. So if we want to generalize, we can say that the landscape of our search space changed drastically from one week to the next, with very slight and common similarities. For instance, this area in particular seems to be the more optimal one, for not just for the 4 ones that I'm presenting, but for most of the landscapes that we visualized and observed. So in conclusion for this work, we looked at the scheduling problem from a new perspective. We studied different mixed policies, which is what we would call a larger class of scheduling policies, which enabled us to move from a discrete to a continuous search space. This allowed us to use continuous search, continuous optimization methods, such as black box methods. Also, we reached the conclusion that determining a good scheduling policy is not very difficult. However, finding the optimal scheduling policy for your current jobs or for the current data that you have is truly challenging due to the volatile nature of data, which is proven by the changing landscape that I just presented. Do you have questions about this work before I move on to the next?
There is one question in the Q&A.
Okay, let's go through the. Okay, sorry. Here. So the question here is
slide 24. Why there is a jump on week 24?
So Salah is answering.
Yes, it's mine.
Parce que tu m'as fermé le truc. Oh, sorry, just wait for a minute here.
1 second. We apologize for this.
And then there is a. Could you explain a little bit the policy? There is another answer, Salah. Oh, okay, or
Okay.
at least we can chat just after, no problem. Maybe you can comment.
Okay. With slide mixed policies. Okay, for the first question, what do you mean by result mixed policies? Tu peux mettre le slide directement, je peux prendre de la main.
Oops. Oh, this slide is here.
Salah, I think he's asking about the spike in performance when we jump from. There's some weeks that there's some spikes between the one week to another. I think that's the question.
Lionel, maybe you can ask your question and precise it online. I open your mic.
Hello, this is Lionel. Thanks for the presentation. Yes, it was on a slide, I don't know which one, but about performance measurement.
Okay.
There's some kind of edge between week 22 and week 24. I was just wondering if it's linked to your method that is presenting some kind of cold start effect, because it did not model correctly until then.
Okay, you said between week 22 and 24. You're saying why there is a week missing between 16, 22, and 24.
No, all performance for all your policies, 3 policies you were showing.
Yes. Okay. Okay.
Was kind of a jump, small jump.
You mean small jumps? All the policies perform the small jump when it comes to the values.
Yep.
Yes, it's probably a very loaded week, because when there are weeks that are extremely loaded, everybody all the value of the target function for all the possible policies will just will become worse automatically. Because there are too many jobs to be executed, the waiting queues will become automatically longer, and regardless of the policy you will use, there will be waiting time.
Okay, I see. Thanks.
Good.
Tu peux arrêter de partager.
Okay, I'll answer the second question now, which is, could you please explain a little about policy learning? What is your actual scheduling policy for scheduling? Okay, seems more like an inception type question, but I will try to answer the way I understand it. Okay. Faut que tu le déroules comme ça. Okay. Feel free to open your mic and clarify your question if you want, because I'm gonna answer you based on what I assume you mean.
Yeah, Muhammad, I opened your mic.
Okay, thank you so much. My question is about actually what type of policy you are defining to schedule your jobs. Like in reinforcement learning, we define some policies, and according to these policies, our agent take decisions, and so we assign some reward to that agent. If they take good decisions, then we assign like positive reward or negative reward. And so I am a little curious. I did not see any policy. What type of policies you
Okay.
are?
Okay. As far as I understood, you come from a reinforcement learning background.
Yes, I am actually.
Okay, basically here, policy is not a set of succession of actions like the reinforcement learning context. For us, a policy, I defined it at the beginning, I think. It's a simple rule of ordering.
Okay.
For instance, in first come first serve, the policy is the one that arrives first gets served first. In shortest job first, the one that is shortest will get served first. It's not a complex policy. It's basically just an ordering rule.
It's just first come when jobs come first, and they serve first, and they next, and okay.
Yes, that's how the term policy is used for scheduling.
Smallest estimation. Okay. Thank you.
Pleasure. Okay, so now let's continue to our to the next work, I suppose. Okay, I will make this slightly faster due to the delays. Okay, the first two approaches that we looked at, the one that I just presented and the one Danilo presented, they try to improve the performance of scheduling by inventing, if quote unquote, inventing new scheduling policies. But in our experience and my personal ones and many people that I talk to, inventing a new policy is generally perceived as extremely risky by system administrators and almost everybody who works on real HPC machines. So for this work, we decided to go on a different direction, but still while still relying on machine learning. Our goal was to maintain the established scheduling policies such as first come first serve, and try to improve their performance or try to improve their decision-making process. Basically, by trying to reduce the uncertainty in the available data. What we, more precisely, we try to improve the estimates of the runtime that are provided by the users. We know that they are extremely inaccurate, so we will try to replace them by our own, by providing predictions. Okay. Before I explain the method, let's take a look at the comparison between the requested runtimes and the actual runtimes. These two curves represent the density or the distribution of both. The upper row is for the requested, the lower row is for the actual runtimes. First, we observe that there are similarities and differences. The differences are quite visible, mainly by the presence of peaks in the middle or at the end of the curve for the requested runtimes, and the almost total absence of such peaks and curves in the actual runtimes. The second observation is for the actual runtimes. We observe that there is a significant peak at the beginning, followed always by an almost flat valley that continues until the end, meaning that there is a large concentration of very small runtimes and pretty much the rest. So one question is in this approach, why don't we just do the most classical thing, which is just try to predict the exact runtime of the jobs. First of all, the exact runtime is very volatile, and it does not only depend on the job itself or the user who submitted the job. It involves external factors that are extremely hard to understand and quantify, such as the state of the machine, the type of the machine, the processor, even the temperature will affect the exact value of the runtime. Okay. Instead of trying to predict them exactly, we opted for a simpler, but as you will observe later, an equally effective approach. Basically, when a job arrives, we determine or try to predict whether it belongs to the peak of the curve that I just presented, which means it's small, or the valley, which means that it's not small. We will label large here. If the job is small, we put it ahead of the queue, regardless of the current ordering policy. If we have multiple small jobs waiting, multiple small jobs waiting, we just order them by their arrival time. The feature we use for classifying the jobs into small or large. We have basic features such as the requested runtime and number of resources. So we have temporal features when the job was submitted. Those are very important because we notice that there are peak activity periods, day and night, for instance, before major conferences, etc., etc. Lag features, our feature important analysis showed that the three most recent similar jobs are the ones that have the most relation with the class of the three previous similar jobs has significant correlation with the class of the job we're trying to predict. That does not mean that the rest of the jobs are less significant, but collectively we know that's significant. So we try to collect them all in a single feature, which we will call mean. Those three. This learning process is conducted again on a weekly basis. Basically, for every week, we gather all the data that we have. We add it to the log, we perform our 3 steps: preparation, extraction, and training, and then we use that classifier for the following week. At the end of the following week, we gather all the jobs we have on the log and we perform the same thing, and so on and so forth until the end of the trace. You can look at it as an expanding window type of learning. Here the learning results for this experiment. For the numbers that I'm presenting right now, we used random forest classifiers to obtain these. The average accuracy between all the weeks and precision and recall seemed to be between 80 to 90%, which are considered quite good if compared to other values in the literature. However, in this case, we are not performing the learning for the sake of learning. The goal has been and will always be improving the performance of schedulers. This figure basically sums up our improvements. The x-axis represents time. The y-axis represents our target function, the cumulative bounded slowdown. The black lines in every curve represent a basic execution of the algorithm without the small large job classification, and the green lines represent the scheduling with the classification. We choose 3 policies to compare: first come, first serve, SAF, SPF, WFP, the ones that I just presented. Okay, without further ado, we can simply observe that our method systematically improves performance by varying gaps for all the studied cases. When there are extremely sharp jumps in the bounded slowdown, our method managed to make them much smaller or even make them disappear altogether. And when there is a slope, we can see this the gap between our using the classification and not using the classifications getting larger systematically. Also, we observe that our method is very close to the optimal. These two represent the optimal case: class clairvoyant and runtime clairvoyant. This is for the total bounded slowdown as well. Our classification methods, both of them, seem to be very close to the optimal values that we can obtain. If you have more questions about this slide or the previous one, feel free to ask me in the Q&A section later. Q&A. Thank you. So do you have any questions? So here are the, oh, probably it's a bit, we have probably time for, okay, here is the kind of summary of the 3 experiences here. So we saw somehow something on the first experience where the time may be very long, and another kind of drawback is that the generated policies are hard to be explained and then to be used by system administrator or the users, because they don't really know somehow how to what happens somehow. And okay, so here it's the same for the second experience. It was if you really want to have the whole search space or the very good one, it's very expensive experience. Actually, what we learn in experience 3 is somehow that a very parsimonic machine learning method is still efficient, and this is something that now we would like to discuss with you all. Okay. Just come back to the smart city example here. You have no, okay, we don't have in a city for managing this big HPC platform. We rather have a lot of small devices that interact locally with in the distributed way. I'm sharing now in this AI Institute in Grenoble research program on edge intelligence. And the idea is to do some federated and distributed learning in a green way, in a way not to use too much computing for this. So I'm targeting edge computing and IoT sensors, where and this is much harder to handle than HPC platform, because a lot of things are moving on and interacting at very low level. Okay, now just let me just comment. This is something taken from the report of the SHIFT project. So we are here on this line here. This is 2020. Here we are here. And 13 per person is the number of IoT that we have in average per person. And this is the growth of all the digital component. And you see that somehow this is the growth is not expected to be that big in regard to what we have now, which is a good news for somehow for the climate. But the IoT is completely crazy and goes through exponential growth. And this is here the expectation is that we multiply by 3 in 10 years. Here this is 2030. So and what is very interesting in the report of the SHIFT, which is also the conclusion of some other reports on some think tank or collective work on some green IT, that most of the IoT or sensors are dedicated, are not really useful. They are on the best available for some comfort, so just to have maybe a better life, but not very mandatory, or simply for fun, or simply completely wasted and stupid applications. So this is something that I would like you to have in mind. And now I'm opening another question about ML, machine learning. This is what I call the dark side of the AI. Okay, so here again, this is something that all these data are coming from recent reports. So they are all converging, okay, more or less to the same numbers and conclusion. Okay, so here first, I would like to recall that ML obviously is now a basic technique that everyone should know because it's everywhere. Okay, so this is good, and there are a very positive effect of ML. So we are still working on this in my Edge program, but
most of the time, this is also a very, very heavy cost from the viewpoint of the power consumption, and then the impact over the negative impact over the environment, and not only emission of CO2, but also for the all what is behind the use of IT. And from the beginning of the revolution of machine learning, we see that if you are looking at the most time-consuming, CPU-consuming computation regarding ML, it doubles every 3-4 months. That means, so you think about AlphaGo or any other well-known program that are very, very time-consuming and that are running all the time in order to improve something. And this exponential growth is very, very heavy because compared to the Moore law, for instance, this is every power of machine doubled every 2 years. So here, it doubles every 3-4 months. So it's completely huge. And if you count from the very beginning of 2012, I did a calculation. This is multiply all this has been multiplied by 300,000 times. So this is something that is completely under control for myself. So this is something that I would like to share with you. So now we have a trade-off because clearly, again, AI and ML are very useful in many strategic complex problems that could probably not be solved without any help of ML. I'm completely aware, and it's very useful for the world and in health. Think about something even for the strategy over climate, just to simulate something. So it's important. And this evolution, hopefully, is completely led now with more and more accompanied by some what we call the green AI. That means people are trying to make better AI from the environment, like the edge, for instance. When we are doing some federated learning or distributed learning, this is done completely close to the chip where the data are produced, and somehow you avoid a lot of data movement in all the networks, and it's much safer, much greener. Okay, but now the problem is again that we cannot control this evolution as it goes. Remember the factor of the exponential growth of IoT, of sensors, of all these small smart devices, and we have what we call the Jevons effect. So I don't know if you are aware of Jevons effect. So you can go here. We put the Wikipedia link to the Jevons effect. It was so what does it tell here is simply when you change a technology, probably this technology point to point improves something. But as the usage of this technology is involving a lot of much more people, then the global synthesis is that at the end you lose because too many people are using this who were not using before. And here you have somehow in AI 2 kind of cumulative Jevons effects that are both on the number of users that are using, which is now completely crazy. I had some workshops with artists last month where they are now doing AI for creations, and a lot they are investigated. This is the role of artists maybe, but everyone is using ML. And so this is the number of users that is increasing and again in an exponential rate. And then you have also the volume of data per user is also completely increasing a lot. So then what we can maybe say is that the growth is far greater than the positive effect. So that this is a question here that we have to in mind. And this is the last message of our talk just before the discussion. We will want to question the utility versus the futility. What does it mean? It's somehow we are developing some ML solutions, so some machine learning solutions, or even some solution in in operational research that are very costly. But we have always, before going on new, we just have to think about what is the collective benefit of this somehow. And for answering, maybe as a basis of the conclusion, maybe we draw some common sense rules. So first, don't forget that ML has a big impact over the environment. Okay. So then, to behave well somehow, we have to educate us, because we did not knew this before with all my students. So that the use of ML costs a lot in terms of emission of CO2 and bad impact of the climate. So we have to control our usages, and probably we have to start by incentive mechanism here. But probably this is not enough because this is very hard to change the mentality of people. So then we have probably to also impose in a big machine, we have to impose some rules not to use too much energy, too much power, or simply be coercive like this. And obviously here, maybe the best is before going on a new development, just ask, okay, what is it or not useful for the benefit of everyone? And if it's not, don't go and don't develop. So we have to, I'm discussing this with people in companies. They are aware of this. So this analysis is quite shared by a lot of people, but we really have to change our habits here and asking ourselves before developing. Okay, this is just these rules that serve as a kind of take-home message, as concluding remarks of this talk. So now we are ready to discuss with you, and we'll be happy to answer your questions.
Thank you, Denis. I think it's not only a good conclusion for your lecture, but it's also a good concluding remarks for the entire school on machine learning. So now if you have some questions, don't hesitate. We have 10 minutes left before the end, the official end of the lecture, so we can have plenty of questions. So go ahead.
So we expect questions, so don't be shy.
Well, maybe I have one. At some point, you mentioned that you were considering only HPC architectures because it makes things simple, maybe for obtaining results in scheduling point of view and scaling research. What does the other type of platform would bring? What difficulties the other type of parallel computing platforms? You mentioned the cloud or all your list. What would this bring as additional difficulty?
Okay, so yes, you're right. HPC platforms again are rather easy because there is a centralized scheduler. That means you have together all on one point, and it's much easier to take a decision. And it's a rather stable platform in terms of resources because the number of processors usually does not move too much. Maybe there are some crash, but this is the amount of memory is always the same. So this is much easier to handle, and all the parameters can stay constant during the whole process. Now we are interested in my group in working on very on completely distributed platform now with edge computing. So edge is simply something that is at the edge of the big clusters or big data centers, and very close to the sensors and to the data. And here edge is characterized by very high heterogeneous variety of the component, because you can have a cluster of hundreds of machines, laptops, smartphones, and whatever. So this is, or simply embedded systems. And then as soon as you have your smartphone, you can go and switch off. And then all the devices are also very versatile. And also you don't have a big power. So you have a lot of constraints that are not the same. But fortunately, we succeeded to have some convergence results on purely distributed optimization process. And okay, under some theoretical conditions like convexity, whatever for the moment, but that can be extended to neural networks. We're trying now to extend this to other classes of functions. So we can, I'm confident that we can obtain some nice results from this, but the problem is far more complicated than HPC world. But here, again, in HPC, don't forget that we have also the users that are also part of the game. And this is not so easy because they are submitting jobs, and we have also to take into account the users, which is also the case in the purely distributed federated platforms. So maybe there
Thank you. I think you have questions in the Q&A now.
But I cannot open the Q&A, or I don't know why I see that 3 questions, but I cannot open this from my, I'm sorry. So maybe you have the questions here?
Okay, I have the first one.
Okay.
Which is, have you compared your results with other scheduling techniques and algorithms? Which ones?
Yeah.
Which metrics?
Yeah.
Okay, I will take that.
Yes, please.
I will answer that question. Yes, for the metrics, generally, as far as I observed, most people tend to use the waiting time or the one variation of the slowdown. That's at least for experimental platforms. For theoretical platforms, there is the completion time, but we don't really use it in our context. When it comes to other approaches, there has been comparative work, yes. Basically, what I can tell you that most approaches fall in the same sphere as one of the simple policies that I just presented, SAF. It would appear that beyond that certain level of optimization, doing anything online will yield only minimal improvements. We still don't know why exactly, but that's our observation about the topic. Does that answer your question? Okay.
Okay, so let me answer to the second question. Is from Philippe. Yes, we can. I would like to promote this idea. So it's a very good question because I'm trying to do this, and some community already always give the cost in terms of CPU power needed to realize some experience, which is an idea. Because if you just want to compare cats and dogs, and if it's the equivalent to way back to New York with a plane and so this is somehow something that is wasting time for somehow. So you can have an idea of at least even for you, if you are developing something, if you can honestly say, okay, for developing this, I did a lot of run, and this corresponds to this. You can transform this to your carbon footprint, and then see. And I think it's a very good way. So yes, we try to ask for, at least in journals, to ask for the equivalent of cost of the experiences. Now. Okay, this is Lionel did a remark, so I let you all looking at the remark. You're right, Lionel. Yes. Deep learning, yes, it's okay. I agree. So there are remarks, so we can discuss the remarks, but maybe we'll answer more Oh, it's a good idea. Maybe I will ask in the conference where I'm in the PC. I can ask for the best paper in terms of green. It's a good idea. So now we think about the cloud. Yes.
In terms of green, the best papers will be the theoretical papers. They have zero energy consumption.
Okay, you're right with, okay, for me, there is not big difference between a data center and the HPC cluster. Somehow the machines are more or less the same. So the purpose is not exactly the same, but okay, they differ in the way to have virtual machines or containers or yes, but this is the same problem actually. So you can migrate a VM, yes, from machine to another. But I know that Google, for instance, did a lot of experiments using machine learning in order to help to reduce the footprint of the big data centers. And they just applying simple rules, they gained 30%. And now they have a lot of people working on this. But I think the problem is the same. For me, data center, HPC, this is also time consuming. The problem here is everyone would like to have the whole collection of his or her photo just by asking the smartphone at once. And then that means all this data should be available everywhere, 7 days or 7/7 and 24 hours a day. So is it really reasonable? I don't think so. I can wait for if I'm using some cloud, which is not the case. I always have my photo in a separate device. Okay, this is the change of habits of people. So it's jump to my conclusion and my take-home message. Maybe we have to change our individual habits to be more reasonable. Because probably in all what you store in this data center, again, that are working all the day, maybe you use several % of what you really need, and you want this to have this very like this very fast. So is it reasonable for? I don't think so. Again, reinforcement. We jumped to this reinforcement learning only recently, so I don't have too much. Salah studied this somehow in the. Maybe you can answer, no? So it's how to classify. I think it's something very interesting for online for this remark and. On reward with multi-bandit. So we did something, but I don't have the experience right now to answer to this. And I cannot really classify this as a. Cannot really answer this question. I don't know if the others have.
Yeah, I think from the experiences that we presented, introduced here in this talk, they are not into the reinforcement learning. So we just worked a little bit on the idea of the list scheduling. So how we sort jobs in the waiting queue, and I totally agree that the reinforcement learning seems quite interesting because the actions, for instance, you could think of the actions being the pick a job for the queue. And you can have different strategies in different states of the platform and take different actions. So this is quite interesting. And in this regard, you can use many techniques for this, and including deep queue networks. And well, I did work as much into the subject, but I totally agree that it's totally interesting to go and.
So actually, there are a lot of papers, and including one interesting paper in the last supercomputing conference on this automatic reinforcement learning, as in the process of scheduling jobs in HPC. This batch scheduling with automatic, and they have this retroaction loop for picking the right job at some point. there's some experience maybe that can be proposed.
Okay, so thank you very much. The time is over, so I think we are going to stop the session now. Thank you for your questions to the participants, and also a warm thank to Denis, Danilo, and Salah for their beautiful lecture, and also the profound, let's say, conclusions that should make us all think about the way we are carrying out experiments. There are questions for sharing the link of a paper. I don't know if you have it in your slides, or yeah, in the slide, I think there are links to the paper, so I will make the slides available. And so I would like to conclude now this autumn school, at least on the Zoom system. Would like to thank all the participants for being here, and there was almost at least 100 people at each lecture, which is a great success for us. And this shows that integration of machine learning, constraint programming, operational research technique is a really hot topic. A lot of PhD students ask themselves these kind of questions, and I hope that we helped you in answering partly these questions. So now I would like to say goodbye to all of you, and we can meet, as I said, for if you have some more questions to the speakers, or if you want to discuss together on the Discord platform. So Denis, Salah, and Danilo, I sent you the link to the Discord platform via email. And for the other participants, of course, you have the link on the website since the beginning. So thank you very much, and have a nice weekend. And see you next time, maybe in person in Toulouse, I hope. Bye-bye.
Thank you. Bye-bye all.
See you on Discord.
Yes.